Let us start today's class. The very first topic of today's class is self-correcting option for sequential circuit design. Suppose we are going to design a 3-bit synchronous counter with two unused state. For example, this is the counter state diagram which will start from 000, then 001, then 010, then we'll skip one state, that is 011. So after 010, the next state will be 100, then after 100, 101, after 101, next state will be 110, then after 110 it will jump back to 000, skipping 111. So this counter will act like this way, starting from 000, 001, 010, 100, 101, 110. Again it will go back to 000. Here we can see there are two unused states. One is 011 that was supposed to come after 010, and another is 111. So we have two unused states. Those states can be taken as don't care condition, as I showed you in the previous lecture. Now if we see the state table for this state diagram, we will see this is the state table for this state diagram. We know if the present state is 000, from the state diagram we can see the next state will be 001. If the present state is 001, next state will be 010. For 011 case, next state we don't care, and for the present state is 111, the next state we do not care, because those state will never appear here as per our configuration. Now the problem will occur if the circuit ever goes to one of the unused states due to an error. Then what will happen? As we considered our unused states as don't care condition, so we do not know what will be the next state from this configuration. Now if we want our circuit to have the self-correcting option, then whenever this unused state appear, then it must go into the cycle so that it corrects itself and it starts counting as per our requirement. Okay, that is the self-correcting option. So whenever this two unused state will appear, then the next state should be a correct sequence number so that it can operate normally. Hence the unused states must be incorporated in this state diagram. So we are putting two more states in the state diagram. Due to any error in the circuit, if 011 appears, then the next state will be 100, and once it reaches to 100, it will continue to 101. In this way it will continue as per our normal operation. Again, if 111 appears due to any error or any problem in the circuit, then even though it comes, so it will move back to 000, so it will start from 000 and it will operate like our required counter. So in this way, if we add these two more states, we can incorporate self-correcting options for our circuit. Here we can see two state tables. The left one is constructed without incorporating the self-correcting options, where we can see whenever we have unused state, we are considering don't care condition for the next states. But this state table is constructed incorporating self-correcting option. Here for unused states, whenever we have 011 or 111, these two were unused states, so we are redirecting the next state to its next corresponding value. Suppose after 010 we are having an unused state, that is 011. If due to any error 011 appears, then it will redirect to next corresponding value means 100, and after that it will continue like this way. If 100 appears, then it will go to 101. In this way it will continue. Again for this 111 unused state, if it appears, then it will go to its next corresponding value, that is 000. In this way the circuit has been made having self-correcting option. Now if we design this circuit constructing the excitation table for this present state and next state, then that circuit will have self-correcting options. However, if we design considering this state table where for these two options, that means 0, 1, 1 and 1, 1, 1, these two unused state, if we consider don't care condition in the next state, then the inputs of the corresponding flip-flops can be taken as don't care condition. So the circuit will become simpler, but it will not have the self-correcting option. But here the circuit will be a bit more complex than the previous one, but it will have the self-correcting option. So in this way, we can incorporate self-correcting options in any sequential circuit. Next, we will start a new topic, that is registers. What is register? A register is a group of binary cells suitable for holding binary information. We know in our flip-flop case, a flip-flop can hold a single bit data. So in order to hold n number of bit, then we need n number of flip-flop. A register has two basic functions. One is data storage, another is data movement. When a register is used for data movement purpose, then it is called shift register. Let's see the basic configuration of registers. These are basic configurations of a single bit register using D flip-flop. It's having positive edge triggering activation. When triggering occurs, this data is stored in the output side. To store 1, we need to give 1, and in the clock pulse triggering, the 1 will be stored at the output side. If we want to store 0, so we need to give 0 at the input side of D flip-flop. Then in the next clock pulse triggering, the data that will be stored will be 0. So we can store 1 bit data using this type of flip-flop. Now, in order to store multiple number of data, we need to use multiple number of flip-flops. The data movement capability or shift capability of a register allows the registers to move data in different direction upon the triggering of clock pulse. Let us see the block diagram of different type of shift registers based on their data shifting directions. We have serial in, serial out shift register. That means data will be sent through one input and will be taken out from another output. This is also serial in, serial out, but it's shift left. We have parallel in, serial out. That means data will be fed parallelly and will take the data out serially on each clock pulse. That means in one clock pulse, the data will be fed parallelly, and if it's 4-bit data, in the next 4 clock pulse, will take out each data in each clock pulse serially. Then this is the block diagram for serial in, parallel out. So in 4 clock pulse triggering, all the 4 data will be stored, and in the next clock pulse triggering will take the data out parallelly. This is the block diagram for parallel in, parallel out. This is the rotate right and this is the rotate left shift register. We'll design different types of shift registers using flip-flops. Let's start designing. We'll start with serial in and serial out shift registers, then we'll cover one after another. Well, let's start with serial in, serial out shift registers. This is the basic data movement structure in serial in and serial out shift registers, and this is the logic symbol for a 4-bit serial in, serial out shift registers. The serial in, serial out shift register accepts data serially, that is 1 bit at a time on a single line. Let us design a typical shift register. This figure shows the 4-bit shift registers implemented with 4D flip-flops. This register can store up to 4 bits of data, and each data is stored serially on each clock pulse. So after 4 clock pulse, all the 4 data will be stored at Q0, Q1, Q2, Q3, and in the next 4 clock pulse, the data can be extracted here at Q3 output, which is this point in the block diagram. Suppose we want to store 1011 data serially. So first MSB will be transferred, then the next bit, then the next bit. So at the first stage, the MSB that will be available at the serial input data. In the next clock pulse, this 1 will be transferred to Q0 and 0 will be available here. In the next clock pulse, this Q01 will be transferred to Q1 and this 0 will be transferred to Q0 and next data 1 will be available here. So this will be the case. In the next clock pulse, the Q1 value will be transferred to Q2, Q0 value will be transferred to Q1 and this input data will be transferred to Q0. In this way, we'll store all the 4 data in 4 clock pulse. Now, if we want to extract the data serially, in the next 4 clock pulse, first of all, Q3 will get MSB. Then in the next clock pulse, Q3 will get the next bit of this data. In this way, we can extract our data in the next 4 clock pulse. Next, we'll see the operating principle of serial in, parallel out shift registers. This is the basic data movement in serial in, parallel out shift registers, where we can see data is entered serially and extracted parallelly. This is the logic symbol for a 4-bit serial in, parallel out shift register. We have one data input through which we'll send data serially, clock pulse input, and 4 outputs that are to be extracted parallelly. Let us see the logic diagram, what we have inside this box. Here we can see the implementation of serial in, parallel out shift registers using 4 D flip-flops. As we know the characteristics of D flip-flop, whatever data available at the input side of the D flip-flop, that will be transferred to the output side of that corresponding D flip on every clock pulse triggering. So in 4 clock pulse triggering, all 4 data will be transferred serially, and when the 4th clock pulse triggers, all the 4-bit data will be available at Q0, Q1, Q2, Q3. Suppose we want to send 1011 data like the previous example. First of all, 1 will be available here. In the first clock pulse triggering, this 1 will be transferred to Q0 and 0 will be available in the data input side. In the second clock pulse triggering, this 1 will be transferred to Q1. This is the Q1 value. And 0 will be transferred to Q0 and the third bit will be available here. In this way, if clock pulse keeps triggering, all the 4 data will be transferred here and we'll get the output at a single time, that is Q0, Q1, Q2, Q3, and all are available after 4th clock pulse triggering. This is Q3, this is the MSB, and this is Q0, this is the LSB. We can see 1011, 1011 data can be extracted parallelly from this register. So this is 4-bit serial in, parallel out shift register. This is the operation of serial in, parallel out shift register, and the construction is very simple. I hope all of you understood. Next, we will start designing parallel in, serial out shift registers. This is the basic data movement in parallel in, serial out shift registers, and this is the logic symbol for a 4-bit parallel in, serial out shift register. In parallel in, serial out shift registers, the data is entered parallelly and extracted serially in next 4 clock pulse. Here we can see we have 4-bit data in D0, D1, D2, D3, which are to be sent parallelly in each stage of this register, one output line through which the data will be extracted in the next 4 clock pulse. The clock pulse input will be given here. We can see an extra input, that is shift or load input for this type of register. First of all, we need to understand what is the function of this shift or load input. We can see we have shift and load bar. That means this input is activated for shift when high signal, that means 1 signal is given here, and this input is activated for load when 0 signal is given here. Because the symbol says shift is active high and load, as it has a bar at the top of this, so it's active low. So low signal will activate the load signal and high signal will activate the shift signal. Now, what is the function of this input? When this input is activated for load, even though the clock pulse triggers, in each triggering, whatever data that is available here will be stored in each stage. That means it will load the parallel data in each stage, but it will not shift the data to the output. So when the shift is activated, instead of loading the available data, whatever data that was stored here, that will be sent serially in the serial data output. In this way, it will operate. So load will load the data and shift will shift the data and give the data as serial data output. Let us construct the logic diagram for shift load operation first. Here we can see two AND gates, and the output of these two AND gates are sent through this OR gate. The operation is very simple here. If one of the input of this AND gate is 1, then whatever data available here, that will be available at the output side of each AND gate. Now, this shift or load input is connected directly to the first AND gate and is connected through NOT gate to the second AND gate. Another input is named as shift data, and another of the second AND gate is named as load data. When this shift load input is 0, the 0 will be available directly to the first AND gate, so shift data will not be transferred, and the 0 will be inverted and 1 will be available in the second AND gate, and this load data will be available at the output side, so we'll get that load data at the final output of OR gate. Again, when shift load input is 1, then 1 is directly connected to the first AND gate, and here the second AND gate will get 0. So whatever data that is available at shift data, that will be available at the output side of the first AND gate, and finally that shift data will be available at the final output of OR gate. In this way it works. So in a nutshell, when the input of shift load is 0, then load data will be available. When the input of the shift load is 1, then shift data will be available. And this is the logic diagram for parallel in serial out shift register. Though it looks a bit complicated, but the structure is very simple. If you understand the operation, things will be more clear to you. We have 4 D flip-flop in order to store 4-bit data. So data will be stored parallelly from D0, D1, D2, D3, as we mentioned the operation in previous slide, and data will be extracted serially from this Q3 in the next 4 clock pulses. Now let us see the loading operation first. When the input is 0, here the output is inverted, so whenever the input of shift load is 0, here the value will be 1 as it is passed through the inverter. So one of the inputs of G1, G2, G3 and G4 will be 1 when the shift load input is 0. At 0, load will be activated. Whatever value we have at D0, D1, D2, D3, that will be available at the output of G1, G2, G3, G4, as G1, G2, G3, G4 is activated by this one value that we are getting due to shift load input equal to 0. So D0 will be available at the output side of G1, D1 will be available at the output side of this OR gate, D2 will be available at the output side of this OR gate, and D3 will be available at the output side of this OR gate. At the same time, when we have 0 input, G5, G6, G7 are deactivated because one of the inputs of G5, G6, G7 is 0. So no matter what is the value of other input, the output will be 0 here. So whatever value we have at D1, that will be available at the output side of each OR gates. Okay. So we'll get the D0, D1, D2, D3 values at this point input of first flip-flop, that means flip-flop 0, D1 data at the input of flip-flop 1, D2 data at input of flip-flop 2, D3 data at the input of flip-flop 3. When these 4 data are available here, if we activate shift load option, That means if we give this shift load value equal to 1, so what will happen? This 1 will make the output of this inverter 0 here. So what will happen? This 1 is directly connected to G5, G6, G7. So in the next clock pulse triggering, this first value will be transferred to Q0 as G5 is activated and G2 is deactivated because of shift load equal to 1. So this Q0 will be transferred through this G5 as one of the input of G5 is already 1 as it's having shifting option, so it will be available at the output of this OR gate. So Q0 will be transferred through this line, and the next clock pulse this Q0 value will be transferred to Q1, and in the next clock pulse this Q1 will be transferred to the Q2. In this way all the data can be extracted serially at the output of Q3. So whenever shift or load option is 0, then the data will be stored in each corresponding stage parallelly, and when this shift load option is 1, the stored data will be transferred serially and data can be extracted at Q3 point serially in the next 4 clock pulse. So this is the complete operation of parallel in, serial out shift registers. Finally, we'll discuss about parallel in, parallel out shift registers, which is the simplest registers among all the registers available. So what is the operation? In parallel in, parallel out shift registers, the data input will be done parallelly and data output will also be done parallelly. This is operational diagram for 4-bit parallel in, parallel out shift registers. So all the 4 bits data will be available in the input side. In each clock pulse, 4-bit input data will be transferred to the 4-bit output data. Let's see the logic designing. This is the logic designing for parallel in, parallel out using 4 D flip-flops. All the inputs of D flip-flops are considered as input data for D0, D1, D2, D3, and the output of each D flip-flop is considered as the output of parallel data. So in input data D0, D1, D2, D3, whatever data available here in the first clock pulse triggering, this D0, D1, D2, D3 data will be transferred to the output side. After 1 clock pulse triggering, all the parallel data will be available at the output side of Q0, Q1, Q2, Q3. So this is how parallel in, parallel out shift register works. So far we have covered the basic operation of different types of shift registers. Next we'll start a new topic, that is memory and storage. What is memory? Memory is the portion of a computer or other system that stores binary data. We have different units of binary data, that is bits, bytes, nibbles, and words. The smallest unit of binary data is the bit. The unit that we use to store 1 or 0 single bit data, that is called bit, the smallest portion. And 8-bit unit is called a byte. That means if we have 8-bit combined data, that can be referred as 1 byte. So 1 byte equal to 8 bit. And the byte can be split into 2 4-bit units that are called nibbles, and bytes also can be grouped into words. That means 8 plus 8, that 16-bit or 2-byte data can be termed as word. So a word is specifically defined as 2 bytes. This table shows the relationship between kilobyte, megabyte, gigabyte, terabyte, and petabyte. As we can see from this table, 1024 bytes equal to 1 kilobyte. 1024 byte means 2 to the power 10 bytes equal to 1 kilobyte. And 2 to the power 10 kilobyte, that means 1024 kilobyte equal to 1 megabyte. And 2 to the power 10 megabyte, that means 1024 megabyte equal to 1 gigabyte. And 2 to the power 10 gigabyte equal to 1 terabyte, and 2 to the power 10 terabyte equal to 1 petabyte. So the size of the memory sometimes defined as some value of gigabyte or terabyte or petabyte. In this way it can be expressed, and from this relationship we can determine how many unit bits are present in that particular memory unit. Here in this slide, the basic semiconductor memory arrays have been shown. This is 8 into 8 array, this is 16 into 4 array, this is 64 into 1 array. Each unique box represents a memory cell where we can store either 1 or 0. So we have 1 bit data storage at each memory cell. We can see we have 1, 2, 3, 4, 5, 6, 7, 8 bit data in row, and in each column we have 8 bit data. So we can have one complete byte in each location, that is 1, 2, 3, 4. These are the locations. If we represent these as location, then we can have 1 byte data in each location. This is 8 into 8 array. The location of this will be row number 5 and column number 5. Here we can see this is 16 into 4 array. That means we have 4 bit data in each location and we have total 16 locations. Here we can see 64 into 1 array. That means in each location we have 1 bit single data and total 64 locations are there. For all these three cases, the memory size is same. We can store 64 bit data here, we can store 64 bit data here. That means we have 64 small memory cell incorporated here, and we have another 64 memory cell incorporated here. So this is 64 into 1 array, this is 16 into 4 array, this is 8 into 8 array. This is the physical structure of 64 bit memory. We have 8 into 8 array, total 64 bit memory unit. Now if we want to locate a single bit position, then the address of the blue bit is row number 5 and column number 4. Now if we consider this 8 bit data as 1 byte, then the address of this blue byte is row number 3. Moreover, we may have 3-dimensional array which will look like this. Here we have rows, columns and arrays. Each array contains 8 bit data. So the address of the blue byte, that means 8 bit data, this is the blue byte, is row number 5 and column number 8. This represents 8 bit data which is 1 byte. Hence this memory unit can accommodate 8 into 8 into 8, total 512 bit data. And this is the formation of 8 into 8 bit array expanded to 64 into 8 bit array. We have 8 into 8 bit array here, 8 into 8 bit array here, 8 into 8 bit array here. In this way, total 8 arrays are set in order to accommodate 512 bit memory. Now let us see basic memory operation. This is the block diagram for the basic memory operations, which shows the operating principle of a basic memory unit. The memory arrays that was shown in the previous slide is located here. In each memory we have two options. One is read option, another is write option. When we want to store some data in this memory array, we need to go for write option. When we want to or we need to extract data from the stored memory unit, then we need to go for read option. Each memory must have address lines. These addresses will be located by address decoder. Suppose we have 4 address. So to locate 4 addresses, we need 2 input in address bus, because using address decoder with 2 input we can locate 4 distinct positions. So we can say k number of address bus can locate 2 to the power k number of address locations. For example, for 4 address locations, there will be two address bus. 00 will locate the first address location, 01 will locate the second address location, 10 will locate the third address location, and 11 will locate the fourth address location. In this way, we can locate any address by using this address bus. We have another bus, that is data bus. We can see both side arrows are given in data bus. That means this bus will combinedly act as input and output. While writing data in the memory unit, this data bus will be acting as input lines. So from the registers, the data will be transferred to the memory array. While for reading data from this memory array, this data will have a direction in the outward direction, and whatever we have in the memory unit, that data will be transferred to the next register unit. Let us see the operations using a basic example. In this memory array, we have 8 into 8 bit memory array. In each address location, we have 8 bit data, 1, 2, 3, 4, 5, 6, 7, 8. So total 8 addresses are there. So we can say in each address location we have 1 byte data. We can see some previously stored data is kept in the memory arrays. These are the arbitrary data. Here, in order to locate 8 address location, we need to use 3 into 8 bit decoder. That means if we have 3 input in the address bus, we can locate 8 locations. So if we have 8 address location, we need to have 3 bit address data. Address bus will have 3 inputs. This is data register where a temporary data is kept, which is to be stored in the memory. First of all, we'll go for write operation. Write operation means whatever data we'll have in the data register, that will be stored in the corresponding memory location that is defined by address register. So the data bus will act as input data bus. As we have 8 distinct memory bit in each address location, that means we must have 8 bit data register, and each data register will be connected with each location. Now, if we want to write our data in this 5th location, for example, then the value of address register should be 101. 101 means we know from our decoder knowledge, if 101 is given in a 3 into 8 bit decoder, this 5th output will be activated. When 5th output is activated, all others will remain deactivated. So this line will be activated. So whatever data we have, this data bus is connected with all these memory locations. However, not all these locations are activated. So whatever data we'll have here, this data will be stored here as write operation is on. This is how the write operation operates. Now let us see the basic memory operation for read operation. For read and write, both cases, the address register operation is similar. In read operation, suppose we want to read an 8-bit data from a particular location, any location, to the corresponding data register. So the data bus will act as the output bus. Suppose we want to read whatever memory is stored at location number 3 of this memory array. So what we need to do, we need to choose the read operation first, then choose the address register location. That means 011 will locate address number 3, and whatever data we will have here as read operation is activated, that data will be transferred through this data bus and will be stored in the data register. In this way, we can extract our data that is available in the memory. Here we need to remember that while writing the data, if we have previously stored data, that data will be erased and the new data will be written. While reading the data, whatever data available from the previous section or the previously written data can be extracted in the data register. So these are two basic operations, read and write operation of a basic memory structure. Now let's see how to design these memory structures. This is the block diagram for designing memory unit. If you understand this block diagram, it will be very easier for you to design any particular size of memory unit. First of all, we can see there is n data input lines and n data output lines. The value of n depends on the number of bit per address. If we want to store 8-bit data in each address line, then the value of n will be 8. So to locate 8-bit data from the registers, we must have 8 input lines, and to read 8-bit data, we must have 8 output lines for 8-bit memory unit. If it's a 16-bit data per address, then the value of n will be 16, and the input lines will be 16 and output lines will be 16. These are the parallel lines. Now each 16-bit data can be defined as word, and if we have k address lines, from the decoder operations we know, using k address lines we can locate 2 to the power k number of locations. So we can store 2 to the power k number of words in this memory unit, and each word will contain n number of data. So here we can see n bits per word, and we can locate 2 to the power k number of words, and we'll have read option or write option. If we activate write option, then whatever data we have available here in the input lines, that will be stored in the corresponding address location, and the address location will be defined by address lines. If we activate the read operation, then from the corresponding address location the data will be read. For example, if we have 8-bit data per word, and if we have total 4 8-bit data, the size of the memory will be 4 into 8. 4 into 8. What does it mean? We have 4 address locations, and in each location we have 8-bit data. To locate 4 locations, how many address lines are needed? We need 2 address lines. Using 2 address lines, we can locate 2 to the power k number of words. That means 2 to the power 2 words, which gives us 4 words. As we have 8-bit per word, in order to read the data from any particular location, we need 8 data output lines. Let us see an example to clarify this idea. Suppose we have 1k into 16-bit memory. 1k into 16-bit memory, what does it mean? It means it has 1k address locations, and in each address location there is 16-bit data. What does 1k mean? 1k means it's 2 to the power 10 bit. That means we have 1024 memory locations, and in each locations we have 16-bit data. So if we draw this in the block diagram, in the memory content we have 16-bit data in each location. These are the locations 0, 1, 2 up to 1023. Total 1024 number of locations. In each locations, how many bits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So total 16-bit data in each location. And the binary values of memory locations is this, containing 10-bit data, starting from 10 zeros, then 9 zeros, 1, in this way 10 ones, which represents 1023, this value. So in this memory contents we have 16-bit per address, that means 1 words per address, and we have total 1024 number of address, that means 1 kilo address. That's why it is called 1k into 16-bit memory. I hope it's clear to all of you. Now, if you are asked what should be the size of the input and output data bus, as we can see, in each location we have 16-bit data, so we must have 16 data line for in and out. As we saw from our previous slide, that the data line should be equal to n, and it depends on number of bit per word. So as we have 16 bit per word, so there should be 16 lines in data bus. How many total words are there? we have 1024 words, that means 1024 locations. In order to locate 1024 location, how many address lines should be there? So we know 2 to the power 10 equal to 1024, where k is the number of address lines. So 2 to the power k equal to number of address locations. Here 2 to the power 10 equal to 1024. That is the number of address locations that matches with our given value. So the number of address lines that is required to design this memory unit is 10, as the value of k equal to 10. So finally, this memory unit has 1k into 16-bit capacity. In another way, we can say 1k into 2 into 8-bit capacity. We know 8-bit equal to 1 byte. So we can say this memory has 2 kilobyte storage capacity. Now let us start designing RAM, that is random access memory, with different storage capacity. First of all, we need to understand what is RAM. A RAM is a read or write memory in which data can be written into or read from any selected address in any sequence. In random access memory, when a data unit is written into a given address in the RAM, the data unit previously stored at that address is replaced by the new data unit. So previously stored data will be erased and the new data will be stored. When a data unit is read from a given address in the RAM, the data unit remains stored and is not erased by the read operation. So while reading data from any particular location, the data will not be erased. This is the designing of a basic 1-bit RAM unit using RS flip-flop. We know the operation of RS flip-flop. In this RAM unit, we have 1-bit input data line, 1-bit output data line, 1 read or write option, and 1 is select option. That the function of this select option is that whenever the select option is enabled, this unit will be enabled for reading or writing operation. If it is disabled, this unit will be disabled for both reading and writing operation. Let us see the operation. First, we start with select input. If select input is 0, what will happen? This is connected with one of the inputs of this AND gate and this AND gate. So both the AND gates will be disabled. So what will happen? Inside this RS flip-flop, both inputs will be 0, 0. And Q output have the previous value. As select input is 0, so here the output data will also be 0. So whenever select input is 0, what will happen? Whatever input data we have here, that will not be allowed to be transferred, because another input of these AND gates are 0, because select is 0, and whatever data that is available at the Q side, that will not be available at the output side, because select option is 0. That will make the output always 0. So in short, we can say if select input is 0, both the inputs and outputs will be disabled. That means this RAM unit will be disabled. Now if select equal to 1, it means this AND gate and the output AND gates, all the AND gates are getting one input from the selected input. Now the output of the AND gate depends on other inputs. Now another input we have that is connected with read or write option. If this read or write option equal to 0, that means the writing operation will be enabled. What is writing operation? Whatever we have value at the input data, that will be stored at the Q output. In read operation, whatever data that is stored in Q output, that will be available in the output. So let's start with the write operation first. If we give 0 input, while writing, the data will not be read. If we give 0 input, one of the input of the output AND gate is 0. So output will be always 0, though we have different value at Q. Whenever write option is enabled, that means this input is 0. There will be no output. That means output will not be read. Rather, both the inputs of these two AND gates will get 1, because this option is 0. Inverted value of 0 is 1. That will give 1, 1 in both the AND gates at the input side. Now whatever input we have here, that will be available here at the output side. Suppose if we have input equal to 1, that 1 will be available here. If it's 0, then 0 will be available here. As input is inverted and sent through another AND gate, so if S equal to 1, if input equal to 1, S equal to 1, if S equal to 1, R will be equal to 0. If input equal to 0, S equal to 0, if S equal to 0, R will be equal to 1. So how it operates: when select equal to 1, write operation is enabled. That means this input is 0. So if we give 1 input, this 1 will be transferred to the set input, and whenever we have set input, then the output Q will be 1 set. Again, if you give 0 input, then here 0 will be available at S input and 1 will be available at R input. That means the output will be reset. That means whenever we will give 0 input, that will be written at the Q. So during the write operation, if we give 1, Q will be 1. If we give 0, Q will be 0, provided select option is 1. Now in the read operation, how it operates: when read equal to 1, these two inputs will be disabled, even though select is 1, but these two inputs will make the AND gate disabled, because whenever we have 1 here, the inputs of these two AND gates will be 0, as 1 is directly connected with this output side. So we have select equal to 1, this read operation is 1, so whatever data we have here, that will be available at the output side. That means we are reading the Q value. In this way, we can read or write 1-bit data in this RAM unit. So this is the basic block diagram for RAM unit. Inside this box, we have this circuit. We have select option, input, output, read or write option. If select equal to 0, even though we give any input, that will not be written here while we are having writing operation. If select operation is 0, if we give read operation, even though there is a stored value, that will not be available at the output side. But when select equal to 1, then if we provide write operation, then whatever value we have here, that will be stored. If we give read operation, whatever the stored data that is available inside this memory, that will be available at the output side. This is the basic operation as I described in the previous slide. Let's design a 4 into 3-bit RAM. First of all, we need to understand what is 4 into 3-bit RAM. This expression represents that there are 4 address lines, that means 4 locations. In each location there is 3-bit data. The total capacity of this RAM is 12-bit, and there are 4 address locations, and in each address location there are 3 bits. So what is the number of input data line and output data line and the address lines? We need to recall this block diagram. As we have 3-bit per location, that means there will be 3 data input lines and there should be 3 data output lines. And to look at 4 addresses, we need to have 2 address lines, and there will be read operation and write operations. Let us start designing a 4 into 3-bit RAM using single bit RAM unit that we designed in the previous slide. This is the 4 into 3-bit RAM designing using single bit RAM cell that was designed in the previous slides. We can see we have 4 address locations, 1, 2, 3, 4, and in each address location there are 3 bits, 1, 2, 3. For each RAM cell, we are using the common pattern that was shown in the previous slide. That is, this is the select button, the top one. This is the input button. This is the read or write operation option, and this is the output option. For all cases, the input, output, read and write operations are similar. This is address bus, and this is 2 into 4 decoder to locate 4 addresses. As we have 4 addresses, we can see. So to look at 4 addresses, we are using 2 into 4 decoder. Now these decoder outputs will be connected with select button of each RAM in each word. Suppose we have 4 into 3-bit RAM, so in each location there are 3 bits. The select button of all these 3 bits will be shorted and it will be connected with this decoder output. So when 00 is given in the address inputs, what will happen? This D0 will activate this RAM cell, this RAM cell, this RAM cell, and this RAM cell. Others will not be activated as D1, D2, D3 are giving us 0. Now the data inputs. This is the least significant data input and this is the most significant data input. We will have 3 data inputs as we have 3 bit per address location. So what will happen whenever we have data input that is available here, suppose 101, the least significant bit will be available all the RAM cells in the first column. The second bit will be available all the RAM cells of the second column, and third bit will be available in all the RAM cell of the third column. But this input will not be transferred to all this RAM cell. That input will be transferred to the corresponding input of the activated decoder output. Suppose D0 is activated, so this select button is on, this select button is on, this select button is on. So whatever input we have here, that will be available and that will be inserted. If the write option is enabled, then whatever data is available here, that will be transferred to the RAM cell and corresponding data will be stored to each location. In a nutshell, if we have 3-bit data, all these 3-bit data will be available in this column, in this column, in this column, but all these 3 bits data will not be allowed to be transferred to RAM location unless or until that RAM select button is activated. That RAM select button will be activated based on the address input. Suppose we want to store a data to this location, so address input should be 10. 10 will activate D2, so D2 will be selected, others will be deselected, that means deactivated. Though all the input data are available, there are corresponding RAM cells, but as other RAM cells are not activated, so this data will be transferred to the corresponding RAM cell if write operation is activated. Now once they are stored in any particular location, suppose we want to extract the data, in that case we will have to have read operation activated. Whenever the read operation is activated, whatever value that is available here, that will be present at the output side of corresponding RAM cell if select button is activated. Now if we want to read the data from this row, what we need to do, we need to give input 01. So D1 will be activated and read option is activated, so whatever data we have here, that will appear at the output side and that will come in the output side through this OR gates. I hope you understood. The operation is very simple. If you understand this part, then you will be able to design any size of RAM. Suppose if you are asked to design a 8 into 8 bit RAM, so to locate 8 locations you need to use 3 into 8 bit decoder, and there should be 8 data inputs line and 8 data outputs line, and in each row there should be 8 distinct RAM cells like this. Here this input is considered as memory enable, because if it is disabled, this decoder will be disabled. Whenever this decoder is disabled, whatever address input we give, all time will get D0 equal to 0, D1 equal to 0, D2 equal to 0, D3 equal to 0. So in that case, if all the decoder output is 0, this RAM will not be functioning. So sometimes this memory enable is considered as chip select or CS. That means if it is 1, then this portion will be functioning. If this memory enable or chip select option is 0, then this portion of RAM will be disabled. Now let us see how to design 1 kilo into 8 bit RAM or 1 kilobyte RAM. From the formation we can see we have 1 kilo into 8 bit RAM. That means there will be 1 kilo 1024 number of addresses, and in each address there will be 8 bit data. So how the formation will look like? This is the block diagram. Inside this block diagram there will be RAM cells. We'll have input data. 8 input data will be there. Address lines. How many address lines will be there? In order to locate 1 kilo address, here 2 to the power 10 equal to 1k. So 10 address lines will be there. There will be a chip select, for which this portion, this chip will be selected. If this chip select is 0, then this RAM will be deselected. There will be read write option and output data. There will be 8 output data. This chip select input will be connected with the enable part of the decoder that we are going to use for address bus, that is 10 into 1024 decoder. That decoder will have an enable pin and that will act as chip select, as I shown you in the previous slide. If we see the previous slide, from that designing, if we want to have this 1 kilo into 8-bit RAM designing, we can go here. As we are going to have 1 kilo address, so it will start from here, 0 number address, 1 number address, up to 1024 number of addresses, and decoder that will start from D0 D1 up to D1023, and here there will be 10 inputs. There will be an enable pin, and in each address location there will be 8-bit data. In this example we can see 3-bit data, but for the given example there should be 8-bit data per addresses. In this way we can get that design. However, in the output side, each OR gate will get 1024 number of inputs. Here we have 1, 2, 3, 4 inputs for each OR gate. But for the given example, if it starts from 0 up to 1023, that means total 1024 number of addresses. So from each RAM cell there will be an output and all of them will go through this OR gate. In this way we will be able to design that 1 kilo into 8-bit RAM, and that will have this formation. Next we will design 4K into 8-bit RAM, that means 4 kilobyte RAM using 4 1K into 8-bit RAM. If we see the previous slide, we have 1 kilo into 8-bit RAM formation like this. So if we use 4 1 kilo into 8-bit RAM chip, then we will be able to design 4 kilo into 8-bit RAM. First, we need to understand how many input output lines should be there, how many address lines should be there. As we have 8-bit in each address, so input data line should be 8 and output data line should be 8. And as we have 4 kilo number of addresses, that means it's 4 into 1 kilo number of addresses. We can write 4 equal to 2 to the power 2 and 1 kilo equal to 2 to the power 10. That means 2 to the power 2 into 2 to the power 10 will give us 2 to the power 12. So we need 12 number of address lines to design 4 kilo into 8-bit RAM or 4 kilobyte RAM. Let us see how the designing will look like. This is the designing. We have 1 kilo into 8-bit RAM, 1 kilo into 8-bit RAM, 1 kilo into 8-bit RAM, and 1 kilo into 8-bit RAM. Total 4 1 kilo into 8-bit RAM. Now, all the data lines will be shorted. There are 8 lines, 8 data lines, input and output data lines. All these data lines will be shorted. That if we have 8-bit data, this 8-bit data will be available here, available here, available here, available here. But this 8-bit data will not be passed through any RAM chip unless or until that RAM chip is enabled. Now, each RAM chip will have 10 address lines. For 1 kilo, we will have 10 address lines. All these 10 address lines will be shorted with each other. That means we will have 1 to 10 lines. Number 1 lines will be shorted for 4 cases. Number 2 lines will be shorted for all 4 cases. Number 3 lines will be shorted for all 4 cases. In this way, up to 10 lines will be shorted for all 4 cases. To enable this 4 kilo into 8-bit RAM, we need 2 more address lines. As we came up to this conclusion that we need 12 address lines. So we already used 10 address lines. Remaining 2 will be used to select each chip. That means we are going to use 2 into 4 decoder using address line number 11 and 12. 2 into 4 decoder. If we have 0 0 input here, the 0 will be selected. What does that mean? These inputs are the most significant bit for address lines. So whenever we have 0 0, the 0 is selected. That means first chip is selected, and having these 2 input 0 0, The other address lines can have 0, 0, 0, 0, 0, 0. That means 10 zeros. Then next number will be 9 zeros and 1. So first address will be selected, then second address will be selected for the first chip, because as we are having 00 at 11 and 12, first chip is selected. So though others are getting 0000, I mean 10 zeros, 10 zeros, 10 zeros, but their address location will not be selected because other inputs 1, 2, 3 from this decoder which are connected to chip select, they are 0, so these chips are disabled. Once these 10 address values get one complete cycle, that means when they reach to the value 111, that means 10, 1111 up to 10 number of ones, the next value will be 0, 1 and 10 zeros. So 0, 1 and 10 zeros. Whenever we'll have 0, 1, that means second chip will be selected, and these 10 zeros will start from the next address location. So we can see the first one will have 0 to 1, 0, 2, 3 number of address location. Second one will have 1, 0, 2, 4 to 2, 0, 4, 7 address location. Third one will have 2, 0, 4, 8 to 3, 0, 7, 1. And fourth one will have 3, 0, 7, 2 to 4, 0, 9, 5 address location. In this way, we can design 4 kilo into 8-bit RAM. If you understand, then from this chip, if we keep all this in a chip, then we'll be able to design 64 into 8-bit RAM or 64 kilobyte RAM. This is a task I hope all of you will be able to design. Up to this much today. Feel free to contact me if you have any question.